Looking at the topic of solubility, I wanted kind of one problem to tie everything together. And we're going to look at the solubility of calcium hydroxide in 4 different situations: water, basic solution, acidic solution, and with a complex ion with a Lewis base. So we're going to start out with the basic setup. Again, first strategy, write your aqueous dissociation equation. Our solubility expression for this, we've got the cadmium hydroxide dissociating to give us cadmium ions and 2 hydroxide ions. Our KSP expression for this is going to be products of reactants to their coefficient powers, which in this case, cadmium. And hydroxide is squared there. And that number happens to be 5.9 times 10 to the minus 15th. And I can write that right here, 5.9, 10 to the minus 15th. So this is the basic equation we'll be using for these first 3 scenarios. And we'll have to do a little more work for part D. But let's start with the root idea, which is in water, solubility in water. And sorry, I've got this new paper that has folds in the middle, so we get these shadows. Anyway, setting this problem up in water, it is the standard type of solubility problem. We can set it up ice. Not worried about our solid. I am worried about our cadmium ions. And for the first problem anyways, the hydroxide is present in water at a concentration of 10 to the minus 7th molar from the autoionization of water. That'll change with these 2 problems, but for right now, when you have water by itself, it autoionizes to give you this concentration of hydroxide and hydronium. So we're going to start with that. Sometimes it doesn't come into play. Most of the time it doesn't come into play, but sometimes it does. The change in this particular case, our solid, everything's going to shift towards the 0 in an equilibrium system. There's our 0, so this has to go up. For solubility problems, we make that an S. This is going to have to go up, and via stoichiometry, that's a 2S. So our equilibrium concentrations must be S and 10 to the minus 7th plus 2S. And there's a lot of discussion about whether or not you should come up with shortcuts for ignoring the 2S or ignoring the 10 to the minus 7th or whatever. But modern calculators make things so easy, I don't even think it's worth the discussion. Just punch it in, use solver. All right? So we can plug this in and get our answer, right? The cadmium ion concentration is supposed to be S, right? And the hydroxide ion concentration is 10 to the minus 7th plus 2S quantity squared. And that's going to be 5.9 times 10 to the minus 15th. And when you solve that, you end up getting that the solubility for part A here is 1.1 times 10 to the minus 5th molar. And a quick discussion or a quick note about that, that will end up the same as the concentration of cadmium ions in solution. And that will end up, or double that, will end up the concentration of hydroxide ions. But what molar solubility is saying is that 1.1 times 10 to the minus 5th moles of this solid species will dissociate in 1 liter of water. All right. So when you're talking about solubility, you're not directly, explicitly talking about the products. You're saying how many moles of that solid are going to dissociate in solution. And the answer for part A, 1.1 times 10 to the minus 5th. And that'll be our baseline number here, is that solubility in water. And that's not super soluble. All right, in fact, if you look at solubility tables, that's a pretty good indication it's not soluble. All right, so we will skip ahead now. And I'm going to use this same equation right here. And we'll see about drawing a line across, so I can just do ice in a different color. I'm going to use this same equation, and there's going to be a big difference here for this pH 10. When the pH is 10, we've got a hydronium ion concentration of 10 to the minus 10, and we have a hydroxide ion concentration of 10 to the minus 4. So that's some acid-base stuff. And I can sneak it in over here, or we can just have that discussion. It happened, all right? pH is 10 to the, 10 to the negative pH is our concentration H3O plus, and we can get our POH as 14 minus that. 10 to the minus POH is going to give us concentration OH minus. So there's a few words that I must have neglected to write. And one of those words here is buffered. And that's going to change the problem a bit. The word that I neglected to write here for part C is buffered. And that's going to change the problem a little bit. Okay, let's set this up then. I'm still not worried about those things right there. My cadmium ion concentration is 0 in the beginning as before, except now we have a specific hydroxide ion concentration buffered at 10, which is a basic pH, and 10 to the minus 10 would give us 10 to the minus 10 molar H3O plus, which is 10 to the minus 4th molar OH minus. 10 to the minus 4th molar for our OH minus concentration. And let me say that again in slow-mo. pH 10, end up with this concentration of hydroxide. It is buffered, so here's where things get special. My change is going to be 0 here because it is buffered. Buffers are mixtures of weak acids or bases and their conjugates, and they resist changes in pH. And so the whole point of having us buffer this solution is so the pH doesn't change, so this concentration doesn't change. It ends up 10 to the minus 4 molar. If this were not a buffered solution, we would expect some change there, but it's buffered, so key wording, that's not going to change. This is still going to go up by S, and it'll end up S, and then we've got these two things to plug into our expression. Our 5.9 will have S, 10 to the minus 4th quantity squared, 5.9 times 10 to the minus 15, and the solubility we get there is 5.9 times 10 to the minus 7th. And this is a common ion effect situation, and that's why I chose specifically hydroxide in a basic solution. Our solubility has gone down, right, by 2 orders of magnitude, 2 powers of 10, and it did that because of the common ion effect that we talked about in another video. And what I mean by that is, here our concentration of hydroxide was 10 to the minus 7th, which gave us a certain amount of resistance to going in that direction. It's going to shift to make the 0 go away, but anything here that's greater than 0 is going to make it harder and harder to go in that direction, right? Because this times this squared has to be our 10 to the minus 15th. Well, 10 to the minus 7th turns into 10 to the minus 4. A bigger number here is going to make it harder to shift in that product direction, and we're going to end up with a smaller number here, all right? And we did, 10 to the minus 7th. So considerably less soluble in base. Again, no surprise because this is a basic salt, so basic salts less soluble in base, acidic salts more soluble in base, basic salts more soluble in acid. And we'll see that here with part C. In part C, we have the solution buffered at pH of 6.50. I picked 6.50 because the numbers got ridiculous when I picked lower pHs. That's barely acidic. I mean, depending on your opinion, it's not a super acidic solution. We're again going to start with a 0 here, but our concentration of hydronium ions is 10 to the negative 6.50. So our concentration of hydroxide ions is 10 to the negative 7.50 at 25 degrees Celsius anyway. So this will be 10 to the negative 7.50. And our concentration is going to go up by S there. It is going to stay the same right there. And so our equilibrium amounts are going to be S and 10 to the minus 7.50. It's kind of worth noting that 10 to the minus 7th and 10 to the minus 7.50 seem like they're really, really, really close, but the difference is this word that I forgot to write in the beginning, this buffered. So this was 10 to the minus 7th, and it increased during this dissociation. This is 10 to the minus pretty close to 7th, and it doesn't change because the solution's buffered. So we've got a slightly different scenario there. Plugging in our equation, it's going to be S times 10 to the minus 7.50 quantity squared, 5.9 times 10 to the minus 15th, and our solubility here for scenario C is 5.9 molar. Huge difference in solubility there in an acidic solution. And I don't know if it's worth writing, but, well, what isn't worth writing, yeah? A nice rule is that acidic salts, less soluble in acid, due to that common ion effect, and more soluble in base. Correspondingly, basic salts have the opposite trend. They are less soluble in base and more soluble in acid. In this particular situation, we have base, a basic situation. That's a solubility of 10 to the minus 7th. In an acidic solution, our basic salt solubility has gone up considerably, 10 to the minus 7th to 10 to the 1st, or 10 to the 0 rather. Unsurprisingly, or as something we might know, cadmium hydroxide is a basic salt, right? So you've got those hydroxides there, that's a big tip-off. Basic salt, more soluble in acid, less soluble in base. And that's our baseline, no pun, right there. And now we're going to look at part D, which is not necessarily a small problem, and we will have to do a bit more work. I think I'm going to do the entirety of that in that space right there. I'm going to have to rewrite this because we have to address the equilibrium system with that complex ion. And the first thing I want to point out is sodium is a spectator. We're just worried about that cyanide polyatomic ion. And we've got the K value for that formation right there. In a previous video, we looked at the stepwise formation of these, but this just happens to be the overall Kf for that. So let's write this out. Cadmium hydroxide. And we're going to dissociate that in water, same equation, Cd2+. And that is one of the equations we're going to need. The other equation we need is the formation of this complex ion. And so let's write that out in one step. We've got cadmium, 2+. And we're going to put that into this ammonia. Wow, in my infinite wisdom here, I wrote NH3, but luckily I wrote the problem correctly and I just had a mental lapse right there. We're not looking at the cadmium ammonia complex. It's going to be the cadmium cyanide. And this charge didn't make any sense anyway. Theoretically, I would have caught that. All right, so we've got cadmium ion plus 4 cyanide ions. Lewis bases, that's our Lewis acid. And we end up with this CdCN4 2- ion. This is our equilibrium system, and I think, like we talked about in a previous video, how does this work? And I think it's really interesting, which is this right here, cadmium hydroxide, is not soluble in water when it's dealing with whatever, water acting as our Lewis base. But if we can throw in a different Lewis base that is better than that water, like this cyanide, all of a sudden the insoluble becomes soluble, and it's a Le Chatelier system, right? This barely produces cadmium ions, but as soon as those cadmium ions form, they get sucked up by that cyanide to make this. So our cadmium ions are getting taken down there and used up, and taken down there and used up, and we keep making more and more of this, and using this up more and more. So that's how these mixed equilibrium systems work, and we had this lavender color. When we look at the system overall, this cadmium ion will cancel out. We're going to add these together linearly, and we'll have our new equilibrium system, which is the cadmium hydroxide in 4 cyanides, giving us 2 hydroxides and then that cadmium complex ion. And we can look at our equilibrium systems in a few ways. I want to put these numbers that we had up here, our KSP, which is going to be the cadmium ions and the hydroxide ions, is 5.9 times 10 to the minus 15th. And our K of formation for this complex ion, which is, as you see it, products over reactants to their coefficient powers. Cadmium cyanide over the cadmium ions, and the cyanide ions to the 4th power, and that is 3 times 10 to the 18th. And if you think back to some previous videos, the K for this combined expression will be the product of these K's. But let's get this written out, and we'll hope I have room to do so. The K for this expression is going to be products over reactants to their coefficient powers. So we've got that hydroxide polyatomic ion, our cadmium cyanide complex over those cyanide ions to the 4th power, and this is to the 2nd power for that hydroxide. And this K is our KSP times our KF, and that's 5 times 10 to the minus 19th and 3 times 10 to the 18th, and we end up with 1.77 times 10 to the 4th. All right, so our solubility of the complex ion here wins that tug of war, that battle over the equilibrium, which you would kind of expect because the Kf is a little bigger than the Ks, at least by a few orders of magnitude. Whew. All right, so in this problem here, plain old solubility in different pHs or whatever, we had no cadmium starting out, and then our hydroxides changed. Now we're not even worried so much about the hydroxide anymore, but we can plug that number in when we're looking at this. So let's do so. I'm out of good colors here. We'll try this to give some distinction. I'm not worried about this because this is our solid. Our cyanide ions are going to be 1.75 molar. This is 1-to-1 dissociation, so I've got 1.75 molar, which for all practical purposes isn't changing at all. Our hydroxide ions are going to start out at 10 to the minus 7th molar, again from that autoionization, and we haven't made any of this yet. All right, moving down then, our change, this is going to have to go down by 4 times our solubility. This will go up by 2 times our solubility, and this is going to just go up by whatever our solubility is. That gives us 1.75 minus 4s, 10 to the minus 7th plus 2s and s. And again, there's mathematical shortcuts you can do, assuming values are small or whatever, but it takes very little time to just plug that into the calculator. This K expression, which is our hydroxide ion concentration, 10 to the minus 7th plus 2s, and we're going to square that, times this, which is s, divided by our 1.75 minus 4s, and that is to the 4th power. All right, and I literally just punched that into the calculator. This equals 1.77 times 10 to the minus 4th. Just want to make sure that was on the screen. 1.77 times 10 to the minus 4th, and I got the solubility here as 1.6 molar. So our solubility ended up being 1.6 molar. And that, in the wrong color, is our answer to part D. So our solubility is actually a bit lower than it was in an acidic solution, and that's because of this Le Chatelier shift at acidic pHs. But this complex ion does increase solubility considerably, 10 to the minus 5 to 10 to the 0 right there, which is pretty darn nice. So once again, basic idea, any of these situations, straight up solubility problems, if it's buffered, that concentration doesn't change, whether it's hydroxide or hydronium, and you calculate accordingly. And then for these combined complex ion systems, take a look at the solubility expression, take a look at the formation of that complex ion, combine them, multiply the K values, and it's just another ice problem. And that is the basics of full-scale solubility for complex ions.